Alright, in our first numerical example-ish of working with distributed loads, I gave you a problem statement only because I want you to begin to be able to create pictures from the words and understand what the words mean. We're asked to find the reactions of a simply supported beam of length L with a uniformly distributed load W. What the heck does that mean? Well, we have a beam. Well, alright, got that. What does simply supported mean? It means that we have a pin roller at one end, a roller, what did I just say? A pin support at one end and a roller support at the other. Could be flip-flopped either side. This doesn't say that this beam has an overhang. Usually if you say simply supported beam, you usually mean you put the supports out at the end. If not, then you have to talk about what the overhang length is and if you have it on both sides. The uniformly distributed part means that the load is not a concentrated load but spread out, and with no other information as expressed in this fashion, you'd have to say, okay, it's spread out over the whole length, and the uniform part means it's the same intensity, force over length, over the entire, well, in this case, length. Right? And so we have a beam of length L, and so on and so forth. Right? This is a classic example of a typical floor beam, particularly in a steel-framed building, right? Where the ends don't have significant rotational resistance, and of course, when this beam were to deflect, it would sag down like something like so. That'd just be your typical common garden variety floor beam. Right? And the load would be modeled usually as some sort of distributed load. That'd typically be the case under a design scenario. Right? We're asked to find the reactions of a simply supported beam of length L. Now there's a bunch of things we have to sort of begin to figure out along the way here, but let's first draw the free body diagram of the beam. And then we'll execute some equilibrium equations and we'll find what's being requested. Right, so we start with the free body diagram of the beam, and we're going to put in our potential reaction components. We'd have at the pin two orthogonal ones, and let's call the left end A, so that's AY and AX. We all want A's in the class. And B, there's nothing wrong with B's. B's are good too. We've got the roller support on a horizontal plane, so we have a vertical reaction at B, BY. Why? Because we like you. I'm getting choked up about my hilarious sense of humor. Alright, we have this gravity load that has intensity per length, right? Force per length along the beam. It's uniform. Hey, the total amount of force, if I have a constant, a uniform value, is, well, hey, I know, let's use calculus. Now you're saying, no, let's not. Well, hang with me here. There's a dx, there's your differential. The total force, that effective resultant, would be equal to, well, one little part of that is W times dx. Check out the units. Force over length times length would give us back force. Add them all up. Well, hey, wait a minute. Don't trick me with calculus. That's an integral. I know that. An integral means area. And wouldn't that be the same for a rectangle, as though the height of the rectangle was magnitude W, the length was L? That would be just W times L. Ding, 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 ding. That would, of course, be the actual evaluation of the integral, as well as the common geometric property shape. Where does it act? At its centroid, which we now know how to find in this segment. Well, it is a rectangle after all, so it's not that hard. It's going to be acting at the midpoint. Right? Now, a lot of people will tell you to replace the distributed load with equivalent force acting at its centroid, and that's okay for reactions. It will not be okay for shear and moment diagrams, the variation of internal shear, internal bending moment along the length of the beam. So I don't tell you to do that, because I know what's really going to happen. I know you're smart enough to be able to handle this. Put in a little dash line if you want, indicate the centroid, of what that's going to be, and we know that that total thing will be W times L. That's the effective resultant acting at the center. Now, I don't ever write that little piece there, but at any rate, it helps to sort of emphasize it's not real, it's an effective location. It does happen to also be the center line or center mass of where the beam is located, so long as the beam has a uniformly distributed self-weight. That's interesting. And now let's write equilibrium equations to find our reactions. That should have been underlined too. There we go. Bam, that all looks better. Alright, now we're going to get all kinds of amazing results here. Sum of forces in the x to the right is positive. That equals ax. Set it equal to 0, and lo and behold, well, gee, ax equal to 0. Boring. Not always going to end up that way, but hey, that's the way it is here. Now, someone wants to write sum of forces in the y, but I don't want to do that. I get ay plus by equals wl, and that's one equation, two unknowns. Don't like it. So let's sum moments about point A. And let's take counterclockwise is positive. And look what we're going to get. by times L minus, hey, how much do you think by is going to be? We got a symmetric situation, structure symmetric, load is symmetric, the foundations are essentially symmetric. I bet B is going to be half of the total load. Let's find out. We've got the load magnitude, W times L, times its moment arm. We have to know where the centroid of this is at. That'd be L over 2. It's just that rectangle. That's all the forces we got. Set it equal to 0, and kabwammo. Look what's going to happen. WL squared over 2 on one side, BY over L, or BY times L, is going to give us that BY equals WL over 2. Woo! That's right. BY turns out to be 1/2 the load. Now, don't you dare take sum of forces in the y and prove that AY is 1/2 the total load, because if we screwed this up, we're not going to know. It's just going to be a carryover mistake. And there was never a single parent ever in the world who was okay with you making some mistakes that ended up killing their child because you did some things right. You got to get it all right. And so let's do this independently. Sum of moments about by, ax is 0, but it also goes through that point, so who cares? We got ay times L, and then going the other way, minus WL, the total load, times its moment arm, L over 2, set it equal to 0, and yes, we will find out that ay equals WL over 2 again, acting up. And sure enough, if we check sum of forces in the y, take upwards positive, we'll get WL over 2 plus WL over 2 minus WL. That does equal 0 the way it's supposed to be. We did do that correctly. Yay! Right, now, it's crucial though, do these equations this way. Don't be screwing around with summation of forces in the y because you think it's easy. No, all you're going to do in more complicated situations is end up being wrong and being wrong multiple times. Do it this way, where you're summing moments about either end, so you can get one equation, one unknown, and independently verify that you've got the right numbers.